Okay, so we have this new animal, momentum, that lives in our zoo, and we need to figure out what it does, right? What are its behaviors? What does it like to eat? How does it mate? Really, right? I'm running with the animal metaphor a little bit, but like, what is this thing, momentum? How does it behave? What are some consequences of the definitions we've made? Let's consider in this segment the interaction of two particles. It doesn't really matter what they are, but if you like, imagine them as, well, you can imagine them as refrigerator magnets that repel each other. So one of them, you know what? I'll use different colors. One of them exerts a force to the right on the other, and the second one exerts a force to the left on the first one. Let's call them, I don't know, let's call them A and B. So what do we know is true? At this point, we know that the sum of the forces acting on, and let's stay one-dimensional for now. We could expand this discussion to multiple dimensions if we felt like, but for now, let's stay one-dimensional. The sum of the forces acting on A is the mass of A and the acceleration of A, but we also know that it's the rate of change of the momentum of A. That's the new version with the new momentum definition. And we know similarly that the sum of the forces acting on B is the rate of change of the momentum on B. So those two equations, I think, yeah, those have to be true, right? With the definitions we've made, we have no choice. If we felt like these two equations, one plus the other, what if we keep the left-hand sides the sum of plus the sum of B? And for this point, I'm actually going to keep the vector hats. You know what? I'll just put them back, because I care about the fact that these forces are in different directions. And that one already has one. Okay, cool. Equals, well, now the sum of the forces on A is this expression, the rate of change of a momentum, and the sum of the forces on B is the rate of change of B's momentum. Now, this doesn't look like much. It seems like kind of algebraic busy work. But two really cool things are about to happen. Here's the first thing. If this force, the one that each exerts on the other, is the only force at work, right? If we're not worrying about gravity or air resistance or anything like that, if this is the only force, then the force exerted on A by B has to be, according to Newton's third law, equal and opposite to the force exerted on B by A, because if object A exerts a force on object B, then object B exerts an equal and opposite force on object A. That's the only way for this to go. If these are the only two forces, they have to be equal and opposite, so that when we add them, we get 0. And this is a very cool result. The other thing, this time derivative operator, it's the same operator, and we know that it is linear. In other words, we can distribute the derivative operator through a sum, so we could write it this way. Okay, so let's unpack the consequences here a little bit. The rate of change of, apparently, the combined motion of the two particles is 0. Whatever the combined motion is, it has to stay that, because it needs to be constant in order that its derivative is 0. Hold on. If force equals dp dt. So imagine we were talking about an object. If we were talking about one mass of some particle, mass or the rate of change of momentum, if the rate of change of an object's momentum is 0, that means that the sum of the forces acting on that object must be 0. In other words, the sum of the external forces acting on that object, remember the word external in Newton's first law? That an object in motion, an object at rest, remains so unless acted on by net external force. And I think we're about to figure out exactly what external really means. If it's just a particle, then everything's external, right? And we never really bothered to unpack what the word external meant, because all the forces were external. If we have a marble, right, and we roll it across the table, air resistance, gravity, friction, normal, they're all external, right? If the sum of the external forces on that object is 0, its momentum is constant. If the sum of the, wait a minute. The sum of the forces that there's a combinedness to this expression that makes me think that we can think about like not just one object anymore, but that we could talk about a combination of objects, a system, a configuration of objects, and that the time rate of change of the motion of the system itself is 0 in this case, because we said there were no other forces acting besides the one between the two pieces. These forces are on from one piece of the system acting on the other, and vice versa. In a lot of ways, they're packaged inside the system as a whole. And the combined motion of the system as a whole can only be affected by forces external, like the marble, right? The marble can be affected only by forces external to it. And it's starting to feel like systems act the same way. That we can move, we can move things around within, but that the total motion of the system cannot change unless there is net external force on the system. Wow. These forces are internal to the system defined of object A and B. Forces act within them, okay, but there's nothing coming from outside to change the total motion of the combination of them. So that motion of the combination of them must have a constant, must have a zero derivative. Okay. So, okay, let me nutshell a couple things. We've said that we can write the momentum of a system as the momenta of its pieces added together. And I suppose if there were more, we would just have additional terms. So I'm just gonna write that it's the sum of the individual momenta. Let's use K. K equals 1 to n. And this summation notation is, again, a mathematical instruction that says for each of the 1 through n constituents of a system, give them an index k, number them from 1 to n, however many n is, 10 or 12 or whatever. For each one, ask the kth element of the system, hey, what's your momentum? Collect the n momenta of those n constituents, add them all together as vectors, and that's the combined momentum of the system. And that just came out of that derivative expression, right? The sum of all the forces is related to the sum of the rates of change of the momenta. So we factor out the derivative and we're just talking about the sum of the momenta. Okay, cool. What if there were other forces acting on A? What if there was, gravity, let's say, force of gravity on A plus the force of B acting on A? And what if there were multiple forces acting on B? Force of gravity on B plus the force of A acting on B. This would be the net force on A, and it would still be related to the change of momentum of the system because we're adding A to B. So this is still equal to what it was. It's just now when we evaluate sigma F, there are more forces to worry about. We can sort of remove these because they are internal to the system that we're talking about. Newton's third law is going to ensure that these are equal and opposite, and they're within the constituents of the system. We know that they're equal and opposite because it's one acting on each other. No one is coming from outside to push on something in a weird way that we can't account for with a third law action-reaction pair, because the thing that exerted the force lives outside the system. All of the pieces that we might ever want to talk about live inside the system, and each of them might exert forces on each of the other ones, but who cares? Those are all internal forces. And we don't care. Newton's third law is going to guarantee that they're all zero. So the only forces we care about, I'm going to extrapolate away from gravity for a second, the only forces we care about are the forces external to the system. If we were able to show, if we were able to claim with some evidence that the net external force acting on a system is zero, then this statement requires that the derivative of the system's momentum be 0. In other words, that the momentum of the system must be constant. And we sometimes use another word synonymous with constant in a lot of ways. But we use a different word because there's a specific event, and we're interested in the momentum before that event and the momentum after that event. So we start with some sort of initial momentum of the system, and then some event occurs. If we can show that the net external force during that event is 0, then the momentum needs to be constant. In other words, the momentum we have after the event needs to be equal to the momentum we had beforehand. Whatever we had, we keep. We don't lose any, we conserve it. If we can show that the net external force on a system is 0, we can rely on the fact that the momentum of that system will be conserved. Whatever it had, it will have later. Part of our job next week is to apply the principle of conservation of momentum to various events. Construct scenarios where we have some event and we can talk about it before and after. And if we can show that the condition for momentum conservation is met, then we can use this principle to say something, to be analytical about that scenario, maybe in a way that we couldn't before. In this case, for example, we don't need to know how much force one piece of a system exerts on another piece of the same system, because those are internal forces. And it's only the external ones that affect the motion of the system. This is cool. We might actually get something out of this momentum definition that we made. It's exciting. This definition, that the momentum of the system is the sum of the individual momenta of its constituent parts, that also is going to have a consequence, and that's something we will unpack in another segment.